Calculus in the Real World, a sports approach by Andrea Gomez. I am a sports fanatic. I love and play all sorts of sports, but my favorite has to be track and field. I recently questioned myself, how did the track designers make a huge football field and still keep a 400-meter track on the outside? How can you maximize the area of a rectangular field if the boundary has to be a 400-meter track? How did the designers come up with the dimensions in the first place? Here we have a standard 400-meter track. The field is made up of a rectangle and two semicircles on each side. The length of the rectangle can be represented as 2r, r being the radius, and the width can be represented with the variable x. What values of x and r will give the field its greatest area while keeping a 400-meter track on the outside? Now, since this is a 400-meter track, the perimeter of the inner field also has to be 400 meters. Therefore, perimeter equals 400 meters. In this case, perimeter is the sum of all sides, so using the variables stated before, we can make an equation representing perimeter in terms of x and r. Since there are two sides of x and two semicircles, perimeter will be the sum as shown. Since we have two semicircles, their perimeter is the same as their circumference of one circle. Now this means the perimeter equation would be 400 equals 2x plus 2 pi r. The area of the rectangle would be a equals x times 2r. X is one side of the rectangle and 2r is the other side. We're using 2r because r is the radius and we need the full side. With this, we need to use the perimeter formula and solve for x. Divide both sides by 2, subtract 200 and x from both sides, and divide both sides by -1. After that, we need to plug in what we got for x back into the area formula. The simplified formula now is a of r equals 400r minus 2 pi r squared. Now we need to take the derivative of a of r. We do this by subtracting the powers by 1 and multiplying them by the constant. The derivative of a of r is 400 minus 4 pi r. In order to maximize the function, we need to set the function to 0 and solve for r. Subtract 400 from both sides, then divide by 4 and pi. The maximum value that r can be in order to get the rectangle's maximum area is 100 over pi. To be sure that 100 over pi is in fact the maximum value, we need to take the second derivative of a of r. If the second derivative is negative, then it is a maximum, and if the second derivative is positive, then it is a minimum. To do this, we just need to take the derivative of the first derivative, 400 minus 4 pi r. After solving, the second derivative is negative 4 pi, meaning that 100 over pi is in fact a maximum. To find the maximum value of x, we need to plug in r into the area formula and solve. While doing this, distribute pi, then divide them out, then subtract 100 from 200, and get 100. The maximum value that x can be in order to get the rectangle's maximum area is 100. In conclusion, to maximize the area of the rectangle inside the track, x has to be 100 meters and r has to be 100 over pi meters. That was my take of real-world applications of calculus. I hope you liked this video and maybe learned a little something new.